Here we have a problem where air is now our working fluid. Air is flowing in a 6-inch diameter pipe at a pressure of 30 psi-G, pounds per square inch gauge, and a temperature of 100 degrees Fahrenheit. If the barometric pressure is 14.7 psi and the velocity is 10.5 feet per second, how many pounds of air per second are flowing? So you need to calculate the mass flow rate of this air. And the important thing to note is that since we're dealing with air, this is not an incompressible fluid, right? This is a gas flow. Gas is a compressible fluid, so the density can change. And so we are going to treat air as an ideal gas at these conditions since we're at low pressure and reasonable temperature. We'll use ideal gas to calculate the molar and mass density, and then we will calculate the mass flow rate. And so we need to get some ideal gas equation information assembled first. So we need the ideal gas constant, and note that I'm going to be working primarily in, well, a mix of SI and American engineering units, but R is 8.314 joules per mole Kelvin. We can look up the molecular weight of air, which is 79% nitrogen, 21% oxygen. That's 28.96 grams per mole. We're told the velocity of the air is 10.5 feet per second, and the diameter is 6 inches. Now, good thing is it looks like the temperature is not changing, and so excuse me, we can. That's certainly good. Another thing that we need to do is we need to convert the temperatures, and so when we use ideal gas law, it's always required that we use absolute temperatures, and so I'm going to convert everything into Kelvin. So this is our temperature of 100 degrees Fahrenheit. Another thing that we need to realize when we work with gases and ideal gas equation is that everything needs to be in absolute pressure. And so that's one of the things this problem is testing you on. They gave you the pressure in gauge pressure, which means it is with respect to the atmospheric pressure. And so the absolute pressure is always equal to the gauge pressure plus whatever atmospheric pressure is. And they told you it was 14.7 psi. And so our absolute pressure of our gas in our pipe is 30 plus 14.7 psi, or about 44.7 psi. We can convert that to kilopascals if we want, and that is 308.2 kilopascals. Now we need to know the mass flow rate, and remember that the mass flow rate of air, that is going to equal what? That is going to be the density times the linear velocity times the cross-sectional area. All right. This density here for mass flow rate, of course, is the mass density. And so we're going to have to first calculate, as we said here, the molar density, use a molecular weight to convert that to mass density, and then we can calculate the mass flow rate. And so we can apply the ideal gas law to calculate the molar density. If we have PV equals nRT, N over V, moles per volume, and this should be a capital V, N over V will be the molar density. So the molar density is equal to P over RT. And so we can do that calculation now. And again, the pressure is going to be the absolute pressure that we have here. And so the molar density of the air at these conditions is 119.214 moles per meter cubed. And you could put that in kilomoles per meter cubed or whatever units you like. We can then take that molar density and convert it to mass density, a mass-based density, by multiplying by the molecular weight. So the average molecular weight of air of 28.96 grams per mole, and we get a mass density of 3.452. Now we can calculate the mass flow rate of the air using that equation that I just gave you above. The mass flow rate is equal to the mass density times the linear velocity times the cross-sectional area. We were given the linear velocity. We can calculate easily the cross-sectional area, and then we can plug all this in and we can get the mass flow rate of air is equal to 0.202 kilograms per second, or in American units 0.444 pounds per second.